right? Because you have like a corner or cousin maybe, right? Okay, and f prime of c is either 0 or d and e. Okay, like you could have, absolute value or a cusp or something. You could have a local max rate point. Okay, that's when you have a critical number. All right. Let's do some very fun examples here. Example. F of x equals 103x plus 1 times the square root of x squared minus 9. Okay. First of all, well, anytime you're given a function, what's the most basic question you ask? What is the what of the function? What is the domain? And also the derivative, yeah, but more fundamentally, what's the domain of the function? All right. What is the domain of that? It's good to find it. Why? In part because we can figure out what legal critical numbers will be. Okay. Of course, if you get a candidate outside the domain, then you got to count. All right. Okay. So let's find the domain of that, first of all. Okay. Now bear in mind that if I ask you to find the critical numbers, okay, sometimes, you can find the domain first. Sometimes, you just kind of play the game, and you just have to make sure that your candidates are in the domain. Okay, so you could say this is optional, although it's recommended. All right, so optional question mark. Okay, sometimes it's hard to find the domain. All right, maybe like here, but you at least have to make sure that your candidates for critical numbers are in there. All right. No, I might ask for it anyway. Okay. Now, so what is the domain of f? What is the implied domain of this function f? All right. Now, the polynomial piece here, this linear piece here, that's not going to cause us any trouble. All right. Well, what is going to cause us trouble is this square root. Actually, if we had a cube root or a fifth root, that would have been easy. What would be the domain? If that were a cube root or a fifth root, there's a polynomial. What would be the domain? It would be all reals. Okay. So the even roots cause us more heartache. Okay. Especially since this guy can be negative, right? That's the problem. Okay. In this class, we keep it real. We never take even roots of negative values. Okay. So, when is f of x real? F of x is real. Okay. If and only if the radicand here, x squared minus 9, is non-negative. What's the square root of 0? 0. Okay, so 0 is okay as long as he's not like a denominator or something, right? Okay, but okay, f of x is real if and only if x squared minus 9, that radicand of that even radical, right? That even root radical, we need that radicand to be non-negative. Okay, so basically the answer to the domain question is the solution set to this nonlinear inequality. Remember that term? Nonlinear inequality. If you forgot that, okay, refer back to my pre-calc notes. Bear in mind, a lot of my most successful students go back and look at my pre-calc notes. Math 141, section 2.7. This is something a lot of calculus people forget or they don't know coming in. All right? How do you solve a nonlinear inequality? Yeah, that's what it is, okay? So in fact, I just did this in my pre-calc class like last week. Okay. Now, a lot of you are going to want to add 9. That's not the best way to do it. Okay? X squared minus 9 is greater than or equal to 0. Let me tell you the easiest way to work this out. Okay, I like the fact that that's a quadratic. Okay, that's very helpful. Let's graph y equals x squared minus 9. Okay, now bear in mind, there are other methods. The sign chart method, the test value method, okay? And I mentioned those in that section. I'll show you the easiest way to do this, especially when you're dealing with a quadratic inequality. Well, how do you graph a quadratic function? As a parabola, okay? I'm going to graph y equals x squared minus 9 as a parabola, and that will give me some automatic information as to what the sign situation is, right? Because remember, when you're comparing something against 0, you're really asking about sign, right? For what guys of x is that guy positive or 0 or negative? That's what we care about. Okay, let's make it very succinct. All right, well. Okay, well, if you're drawing the parabola, right, it would help to know what the real zeros of this are going to be. What do the real zeros correspond to here? Well, oh yeah, and what are they on the graphics? On the x-intercept, right? Okay, so the x-intercepts, okay, correspond to when x squared minus 9 is 0. Okay, now here, you can add 9, that's okay. X squared is intercept at positive 3, comma 0, and negative 3, comma 0. All right, those are x-intercepts. Which way does this parabola open? The leading coefficient is positive. Opens which way? Up. Okay. The y-intercept here is negative 9, but we don't even care. We don't even care exactly where the vertex is. What matters is we care about the pieces of the parabola that lie where? Either above or on y equals 0. Okay? Remember, all this here is y, right? All this here represents y on my graph here. All right? On this graph here. Okay? We want to know where this quantity is positive or 0. So I'm going to fuzz in, okay, the part of the parabola I want. I want this piece. I do want this intercept, okay? Do I want this piece, the smiley face? No, I don't, because x squared minus 9 is negative here. Remember, the y coordinates here give you the value of x squared minus 9 for these values of x, okay? In these cases, for these values of x, like 0, for example, x squared minus 9 is negative in value. For example, if you plug in 0 for x, okay, you get negative 9 here. That's not going to be any good. Okay, so we don't want that. However, over here, for these values of x, the value of x squared minus 9 is positive here, 0 here. I do want that. Okay, so these are the pieces of the parabola I want. What values of x correspond to these pieces of the parabola? When I project on the x-axis, I get this left wing. I also get this right wing. And guess what? That's the graph of the solution set. That's the graph of the solution set. Therefore, that represents the domain of the function. So what is the domain of the function? The domain of the function is given by, what's the left wing in interval form? Parenthesis what? Infinity, comma, negative 3, and we include it, right? Negative 3 is good, right? This is 0, that's good. Union, because we're skipping over a bunch of numbers. Bracket, 3, comma, infinity, parenthesis. Okay, that's the domain. That's two ways. There's a left interval and a right interval. Okay. Now bear in mind, if you had done something like add 9, a lot of people add 9. X squared is greater than or equal to 9. And then, only the very numerically clever can figure out that's this. Okay, that's why it's best to isolate 0. You treat it as a signed problem. If you're comparing against 0, it's a signed problem. Okay. It's easy to graph this. Y equals x squared minus 9. Graphs as a parabola. This one opens upward. I just need to know which way it opens and where the x-intercepts are. Okay. And then in this case, I want to know where this guy is positive or 0. I pick up these pieces of the parabola, including the intercepts. I want to know what x values lead to positive or 0 values for x squared minus 9. Okay, here are the values. Okay, these high values here, these very negative values over there. Okay, that's fast. Now, if you prefer the sign chart method, where you have, x plus 3, x minus 3, do the whole sign thing, that's fine. Test values, right? Test a value here, test a value here, test a value here, that's fine. Because a polynomial function can only change sign at its intercepts, right? Zeros. So that's another way to do it. But I think this is the fastest way, especially for quadratic inequalities. Okay. You can even do it for a third or fourth degree, but you just won't get a parabola. It'll be something else. Questions? We'll spiel there just on finding the domain. And again, if I don't ask for it specifically, it might be optional in the sense that the only thing I have to worry about is that whatever candidates we get for critical numbers, we have to make sure that they're in the domain. Okay. So you could just say, if we have a candidate, try it out. Does he make that guy a real guy? But still, it's a good basic question, right? What is the domain of the function? And I could ask you that. Also, we're going to graph these things. If we're going to graph these things, you better know the domain of the function. These are the only x coordinates we're allowed to graph. All right. Questions about this? Right. Again, you can use the sign chart method, test window method. Look at section 2.7. This is one of those pre-calc topics that no one really knows or wants to remember coming in, but it's one of those little details. Okay, coming in. You have to know it, but very few people remember. Don't add 9. All right. Now, finally, that was pre-calc. What's calculus? Well, someone mentioned it. We found the domain. It's a calculus class. Guess what? We're going to work out the derivative, of course, because we want to find critical numbers, right? So critical numbers, we need to have some sense of the domain, or at least check to make sure that our guys are in the domain, at least, right? Also, let's find the derivative. We need that. All right. Find f prime of x. All right. What rule am I going to need? The product rule. If you didn't know that we needed the product rule, Okay. Even Pope Francis will not help you now. Okay. All right. So how does it go? It goes derivative, copy plus copy, derivative. All right. Derivative copy plus copy derivative. All right. Copy the 3x. No, well, okay, we can take the derivative of 3x plus 1. What's that? That's 3. Okay, again, I hope you know that. I don't want anyone to know. Really? All right. Copy root x squared minus 9. Okay. Plus copy 3x plus 1 in parentheses. All right. Now here's the hard part, right? Working out this guy's derivative. In fact, let's do this first. Okay, derivative of, this is x squared minus 9, all the way to exponent. 1/2. All right. That's the hard part, right? Working out that derivative. Okay. Any questions? The product rule. Okay. Bear in mind that there's no easy way to distribute that. All right. I don't want to quite erase the domain yet. Here. All right. Okay, he is handy to have. Even if I don't explicitly ask for the domain, it may be a handy guy to have. All right. Okay, equals. All right, so we have, okay, 3 root x squared minus 9. I think we're okay here. All right, 3 root x squared minus 9. Right, plus quantity 3x plus 1 times. Okay, here's the hard part. We're differentiating law to the 1/2. What's the first thing I write? 1/2. Law to the, what's the new exponent? Negative 1/2. I'm going to have a tail. All right, now, I copy the base here. X squared minus 9. Okay, the tail's over here. What's the derivative of x squared minus 9? 2x. Okay, the derivative of log of 1/2 is 1/2 log of negative 1/2. The blah, the derivative of the base, is 2x. Any questions? Okay, I hope no one's surprised. At this point, I hope no one's surprised. Okay, the 1/2 and the 2 do kill each other within that term. Okay, let me rewrite this. I'll do it. Okay, just do it. All right, this is 3 root x squared minus 9. Okay, we have a plus sign. All right, we can write this as a fraction. On the top, okay, now the 1/2 and the 2 kill each other off. The x does survive. All right, he survives. So does the 3x plus 1. He survives. Okay, this guy I can write down here as the square root of x squared minus 9. All right, that's pretty good, but we can do better. All right, questions so far? That's pretty good, but we can do better. Questions so far? Questions so far? All right. Now, let's make this a single fraction. Remember that when you're finding critical numbers, it helps you to make this nice. Okay. Now, I know sometimes on the test I was pretty liberal in terms of the kinds of forms I let you give me, but you know it really does help you to make that nice before you think about critical numbers. All right. Let's make it nice. In particular, let's make this a single fraction. That'll help us. All right. I can write this over what? 1. I always can, right? Okay, let's build these up so I get a common denominator. All right. So we have 3 root x squared minus 9 over 1. I want a common denominator. I want that as my common denominator, so I have like fractions. So I'm going to multiply top and bottom by that guy. All right. Root x squared minus 9 over root x squared minus 9. Bear in mind, we're not changing the domain issue. Okay. All right. Plus, okay, x, quantity, 3x plus 1, over root x squared minus 9. Okay, I'm building up this fraction here, so I'm going to get like fractions. Okay. You agree that in the end, I'm going to end up with a common denominator, root x squared minus 9, right? Because the 1 here is not going to do anything. Right? Okay. Questions? We're going to get a common denominator, right? On the top, what happens? We have the 3. What's root blah times root blah? It is blah. Okay, we're assuming that this guy, well, he's going to be positive, right? But okay, but x squared minus 9. All right, 3 times quantity x squared minus 9. Bear in mind, we're assuming this guy's positive anyway. All right, plus, okay, x times the quantity 3x plus 1. Okay, now bear in mind, if we had a minus sign here, and if we had more than one term up there, we really need to work grouping symbols. But we're pretty distribute like crazy, okay? Let's simplify that numerator. Okay, again, you're going to have to do hard work anyway, so may as well do it here, all right? Then on the top, we distribute 3x squared minus what? 27 plus distribute the x. We have 3x squared plus x, all right? All over, root x squared minus 9. Do not engage in wishful thinking. I know that we sometimes see mirages. These do not cancel. What is 3x squared plus 3x squared? It's 6x squared. Sorry, they don't cancel. They become 6x squared. But don't try to see mirages. Okay, 6x squared plus x minus 27 all over root x squared minus 9. And that's pretty good. All right. Now, I have some comments though, but any questions so far? This was pre-calc, but it's tricky pre-calc, right? You did a lot of this in chapter 3, I know. Questions? Questions. We made that very nice, right? Made it a single fraction, made it very nice. Some of you might say, should we rationalize the denominator? Okay, here's the usual rule. If you have a constant like 1 over root 2, you tend to rationalize the denominator, right? If it's your final answer. But if you have like 1 over root x, right? You have a variable radicand. Well, what if x is pi, right? What if it's messed up anyway? You'll never be able to rationalize the denominator. So in a situation like this, we tend not to rationalize the denominator because what if x is like pi, right? You're never going to get it. Okay. So this is fine. That's very lovely, actually. Okay, that's almost as good as we can get it. 6x squared plus x minus 27 over root x squared minus 9. That's as pretty as we can make this. Okay. Questions? Questions? Okay, so it's not ready for, super modeling, but it's good enough. Okay. All right. All right, questions. That's a nice form for f prime of x. Okay. And let's have some questions. Number 3. All right. Oh, okay. Where is f prime of x D and E, or undefined? I know that's not grammatically proper, but you know what I'm saying. Where is f prime of x undefined? Where does it not exist? All right. Now remember, we only care about a critical number has to be in the what of Big Daddy F, the domain of f. Okay. Okay. Where's f prime of x D and E? I should add on the domain of f. Okay. So we're looking at the numbers here. All right. Because you might be going, hey, I'm looking at this guy, look down here. Okay, 0 is going to be a problem, 1 is going to be a problem. Okay, a whole bunch of numbers, strictly between here and here are going to be a problem, but they're dead anyway, right? Okay, I mean, it was pointless, they were literally pointless to begin with. Okay, so the only interesting numbers are numbers in the domain. Now, here's my question. In the domain, it's nice to put it this way, because that's the problem. In the domain, okay, there are 2 numbers that are going to make this guy undefined. Which 2 numbers? Negative 3 and positive 3. Why? Because it makes this denominator 0. Okay? So where's f prime of x, D, and E? Okay. So negative 3 and positive 3, okay, make f prime undefined, or D. Again, again, this is grammatically improper, but let's not worry about grammar right now. Okay. Negative 3 and 3 make f prime D and E. They make them undefined. Okay. And they're in the domain of f. Okay. And they're in the domain of f. Therefore, what are these? These are critical numbers. Okay. So we know that negative 3 and 3 are critical numbers. Why? Because they're numbers in the domain of f, where f prime is D and E. Okay? So wait a minute. They're in the domain of f, but not in the domain of f prime? Yeah. Okay, those are exactly cases where you do get critical numbers. Okay? They're in the domain of f, but they're not in the domain of f prime. Okay? Negative 3 and 3. Now there might be more. Okay? But we know we have these 2 so far. Any questions? Any questions? All right. Okay. Now, where else could we get critical numbers? Numbers in the domain of f, where f prime of x is what number? 0. Okay, so number 4. Right. Okay, where is f prime of x equal to 0? Again, I should say on the domain of f. Okay, so we're only looking at these numbers. But the numbers right in between, they're dead anyway. There's literally no point. So these guys are dead anyway. Okay, there's no hope for 0 or 1 or negative 1. They're dead. Okay, because here's the deal. If you make f prime DNE, you could be a CN. But if you make Big Daddy f DNE, you're not a CN. If you make Big Daddy f DNE, you cannot be a vertical. However, if you make f prime DNE, you might, provided that you don't make f DNE. All right. Let's look at this guy here. F prime of x. Remember, this guy's f prime of x. Now, remind me, when does a fraction equal 0? We first need what equals 0? Which part? Numerator equals 0. All right. Okay, so let's set 6x squared plus x minus 27 equal to 0. I have some good news and bad news. Good news is this guy's a quadratic. We can deal with it. Bad news is if you try to factor him using the old Math 46 techniques, it's not going to work. The discriminant is not a nice perfect square. Let's use the QF. What's the QF? Quadratic formula. I assume you know it. I don't have to write it. When we write it, x equals the opposite of b plus minus the square root of the discriminant, which is b squared minus c all over 2a. Okay? I hope I don't have to write that again. It's good to identify what these guys are. What is a? 6. What's b? Careful. 1. Careful. What's c? Negative 27. Okay, I think that is worthwhile. Identify what a, b, and c are, because a lot of people forget to write 1. A lot of people mess up signs. Okay, so even I do this. It's good to write down what a, b, and c are. All right. Now, I trust you can work this out, plug these in. All right. The discriminant here turns out to be not a nice perfect square. Okay, if this were a nice perfect square, then this can be factored nicely over the integer. It doesn't happen here. All right. Okay, in fact, I'm going to round them off. All right. What are the approximate solutions here to 3 sig figs? We get negative 2.21. Okay. Also, 2.04. Okay. These are the 2 approximate solutions to this equation. Here's my question to you. Are these critical numbers? No. They are not where? In the domain of f. Okay. These are not in the domain of f. So they don't count. Basically, I've wasted your time. Not really. You really should indicate this work, right? These are candidates, but you have to strike the candidates. Okay? You should indicate this. All right? So we have no more critical numbers. Okay? Only negative 3 and 3 are critical numbers. Okay? So the only critical numbers we get here in this example come from cases where f prime is DNE as opposed to 0. All right. And by the way, why are they not in the domain of Big Daddy f? Well, if we look at Big Daddy f, okay, these values lead to negative radicands. All right. Okay. And by the way, these guys these guys technically don't even make the derivative 0 to make the derivative undefined. But the problem is, here's the thing. Let's say you're a number, and you want to be a critical number. We find out that f prime, where you are, is undefined. Actually, you're kind of happy. Hey, I could be a critical number. But wait a minute. How can I ruin your dreams if you're not in the domain of Big Daddy f? Okay? Yeah, then I ruin your dreams. Okay. Technically, these don't even make. Technically, these make f prime DNE, by the way, because the denominators are no good. Okay. All right. Well, we only have 2 critical numbers, and that's it. Yeah, I guess we basically ended the problem, right? We found out that negative 3 and positive 3 were the only critical numbers. By the way, and later on in this class, in this chapter, it's fair for me to ask you this: how do you graph this thing? Here's how this thing graphs. Okay. extrema here, absolute or local? Any extrema. Is this a local min? No, it's not. Why not? There's no neighborhood on which f is defined. There's no neighborhood of 3 throughout which f is defined. Same thing here. Okay, this is not a local max point. And there are no absolute extrema because this guy goes on and on up. This guy goes on and on down. This guy has no extrema of any kind. It is interesting that we have 2 endpoints though.
So our equation is this graph without that, the equation.
This is the graph of y equals f of x. 3x plus 1 root x squared minus 9. All right. Question. I mistray. F of x is secant of x. Let's say you forgot how to graph this thing. What are some hints we can use here? All right. Let's find the critical numbers. All right. Now, here's the thing. You might be going, oh, does that mean we have to figure out the domain again? Actually, here, there's some shortcuts. All right. What is secant of x? It's 1 over cosine of x. All right. Now, what's f prime of x? What's the derivative of secant x? Secant x, tangent x. All right. Secant x is 1 over cosine x. What's tangent x? Quotient I did. Sine of x over cosine x. All right. Now this is very simple, folks. Okay. Now we don't even have to find the domain. We can use logic. All right. Where is f prime of x dne? Okay. When is this guy undefined? When cosine x is what number? 0. You agree? Okay, f prime is undefined if and only if cosine of x is 0. But wait a minute. If cosine of x is 0, can that value of x be a critical number? Can these values be in the domain of Big Daddy F? No. Okay, if cosine of x is 0, guess what? You make Big Daddy F dne. Remember what I said before? Let's say you want to be a critical number. F prime is dne where you are. Yay. But so is f. Boom, you're dead. What does this mean? No critical numbers. In cases like these, we have no critical numbers. All right, no critical numbers in this case. What about where f prime of x is 0? Okay. But now, okay, let's look here. F prime of x is 0. All right. When does that happen? Well, look at this over here. It's when what equals 0? Sine of x is 0. Can sine of x and cosine of x be 0 at the same time? Wait, doesn't sine squared x plus cosine squared x equal 1? Can sine of x and cosine of x be 0 at the same time for the same x? No. Okay, no. For example, the origin is not on the unit circle. All right. Now this one you have to solve. All right. Sine of x equals 0. Let's solve that. Where does sine x equal 0? Here and here. Okay. What are the corresponding values? X equals in, where n is integer. Okay. And these are going to be the critical numbers. Why? Because they make the derivative 0, right? F prime is 0 here. Okay? And they're in the domain of f. How do I know they're in the domain of f? Because if you're making sine of x 0, you know you're not making cosine x 0. Remember? Okay, there's no value for x that makes both sine. Remember the sine wave and the cosine wave? Did they have the same x-intercepts? No. They have different zeros, remember? They're phase shifted. All right, that's another way of looking at it. Okay? So the only time you have that happening is this. Now, how do we know that we have a bunch of critical numbers? What does the graph of the secant graph look like? It's even, right? We start with a cosine wave. VA, 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 VA. How'd it go? Up U, down U. Up U, down U. Up U, down U. What do the critical numbers correspond to? Over here. Horizontal tangent line. Horizontal tangent line. Horizontal tangent line. Makes sense, huh?
Are those also absolute maximums?
No, because this guy goes up, 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 this guy goes down, down, down. But they are local, or relative. Questions? That's a reminder, these are up-U, down-U graphs. Okay? And I'm sure you felt like saying that to me during the test, up-U, down-U.
Professor?
Sounds vaguely profane and mean.
Professor?
Yeah.
If you would take a portion of that graph, say just the middle one.
Sorry?
If you take a portion of the graph, say just the middle U,
Yeah.
would that be the global minimum?
Well, wait, why do we just take the minimum?
I mean, if like just
Well, if hypothetically that's the only part of the graph, yeah, we can absolute midpoint, but it's not.
or would it also be like the
The local also.
and but you won't know the max. I mean the
There is no max because the
it
points
goes
go
up.
up. Range goes within.
Yeah, I was just
Yeah, yeah.
You said prime is 0, so
Yeah.
the part is,
Horizontal tangent lines.
but that's 0.
Yeah, so the zero. Now the turning points. Pi n is where we get the turning points. Slope tangent line. Yeah. The slope of the tangent line is 0. My last deal. How about tangent x? This is our last victim. What's tangent x? It's sine of x over cosine of x. What's the derivative of tangent x?
Squared x.
Squared x. You do that. 1 over what?
Cosine squared x.
Cosine squared x. Well, where are the critical numbers? Okay, well, where is this thing dne? The only way that this guy's undefined is if cosine x is cosine x is 0, right? Okay, but let's say that you have a value for x where the cosine value is 0. Can that guy be in the domain of Big Daddy F? No. Okay. So f prime is dne exactly when Big Daddy F is dne, which means we get no critical numbers in this case, right? Okay, if the only times that f prime is dne is when Big Daddy F is dne, you're not going to get critical numbers in that case, right? So then the question is, what about where f prime of x is 0, right? Well, f prime of x can be written like this, right? 1 over cosine squared x, okay, equals 0. Question, does this have any real solutions? No. Because in order for a fraction to be 0, what part has to be 0? Numerator. Is 1 ever equal to 0? No. Okay, this never happens. Okay, this never happens. Okay, no solutions. Empty set, no solutions. Therefore, how many critical numbers does the tangent function have?
0.
None. No CNs. Now you might be going, wait a minute, I thought they had snakes. I thought snakes went flat. X cubed does, x to the 5th does, not tangent. Not tangent. When you draw tangent, that's the zoo of snakes, right? This guy, this guy, this guy. You look at the origin, and you go, wait, I thought there was a horizontal tangent line. No. No. What is the slope of the tangent line? Okay, it's secant squared at 0. That ain't 0. That's 1. Okay, that's the flattest you get, but that's as flat as it gets. There are no horizontal tangent lines. This guy has no CNs. No local extrema. No CNs. That's 4-1. Is this what you get for?
Straight in this section? That's all for one?
That's 4-1.